Hello scholars, welcome. Mr. Hinkle here. Let's figure out how we distinguish one mineral from another through mineral identification. We will define mineral identification and then look at all the various methods that geologists use to distinguish one mineral from another. Okay, so mineral ID is the process of determining the specific characteristics and properties of a mineral in order to distinguish it from others. I feel like a broken record at this point. This is crucial in geology and mineralogy. We want to know what minerals we're looking at, and if we understand what mineral it is, we can get to tectonic setting, conditions at formation, history, and ultimately getting to this big question of how did the Earth form? How do we understand what Earth history was like when we weren't there? Okay, so mineral identification is a skill that one develops over time, and geologists identify minerals by physical properties. This is important. So we've got mineral ID, and this happens by physical properties. We can perform tests on these minerals in order to understand. Here's the overview, but I would like to go through them one by one. So the very first thing is luster. Refers to the way a mineral scatters light. Okay. Chalcopyrite has a metallic luster because it looks like a metal, it reflects the light. Here, pyrite. Is that too much? Whoa, whoa, whoa. Pyrite, sorry if that made you dizzy, has a metallic luster. Let's go here to starlight, has a dull or earthy luster, which we would say is non-metallic. So if we're thinking about physical properties, we could look at luster as how does the mineral scatter light? And we've got metallic, submetallic is in there, and non-metallic. Non-metallic I believe I have on my next slide, as well as submetallic. Submetallic has lots of different types. Vitreous glassy, quartz, earthy dull. This could be kaolinite, silky, we might say that's gypsum, pearly, like inside a mother of pearl. Submetallic has the appearance of dull metal, like pewter. You might call this, oh yeah, submetallic is going to be the in-between of metallic and non-metallic. So first characteristic is luster. Next characteristic is color. We want to be careful with color. Color is not the most diagnostic property because some minerals like quartz can come in a variety of colors. Red quartz, blue quartz, pink quartz, orange quartz, massive white quartz, clear quartz, smoky quartz. Great, right? Awesome. Fluorite, blue-purple fluorite, orange-purple fluorite, purple fluorite, yellow fluorite, clear fluorite, smoky fluorite, massive fluorite. Right, so quartz and fluorite. If I was trying to distinguish between these two minerals using color alone, I wouldn't know because they both come in so many different colors. Certain minerals, like azurite in the top right corner here, has that distinct blue. Malachite has a distinct teal green. So we don't want to just throw color out, but we want to not only use color when identifying minerals. Streak is the color in powdered form. So I have two minerals here, specular hematite and graphite. Now if we can see, these are both gray minerals. This is a porcelain streak plate, and when I use the graphite on the streak plate, I get a certain color. The graphite makes it gray. And when I use the specular hematite, and I'll try and use the other half of the streak plate, and you could probably hear it grind, 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 grind. What's grinding is the mineral down into colored form. So the graphite left a gray streak, and the specular hematite left a red-brown streak. Streak is the color of the powdered form of the mineral, and it is very useful in identifying. Let's see, powdered form color. Color, we'll put a big question mark there because it can be helpful, but not always. Hardness. You may have heard the saying at one point, the only thing that can cut diamond is diamond. And that is a true statement because of mineral hardness. So mineral hardness is a relative scale from soft, talc, gypsum, calcite, to progressively harder, fluorite, apatite, orthoclase, quartz, topaz, corundum, diamond, with various tests, a fingernail, a copper penny, knife, steel nail, and masonry drill bit. So to exemplify this, I have a nice big slab of gypsum, and I have a fingernail. Gypsum has a hardness of 2. My fingernail has a hardness of 2.5, so that means that my fingernail can scratch into the gypsum. You might hear that scratching sound, and you can see when I wipe away the powder, those scratches are there. Let's look at calcite and quartz. So quartz is harder than calcite, which means that quartz can scratch calcite or calcite can scratch quartz. Yes, quartz can scratch calcite. Quartz, let's see, calcite, and I know these. I will take the quartz and actually, let's bring this a little bit closer. You can see I cut a pretty deep groove into this rhomb of calcite with the quartz. That is because quartz is harder than calcite. So if I've got fluorite and quartz, and I can't tell because of the colors, maybe I try and scratch one into the other, and I see which one is relatively harder, and that helps me identify the difference. For example, hardness is really important, and it is a relative scale, and we look at it by scratching. How does one mineral scratch another to indicate whether it is harder than that mineral or not? Crystal habit. So crystal habit is the way a crystal grows relative to its chemistry. Minerals have a crystal structure, and given the right environment and conditions, they will grow. The mineral starlight growing into its crystal structure. The mineral quartz growing into a quartz crystal. The mineral calcite not growing into its crystal structure, but actually breaking into a specific shape. So this gets a little bit tricky, I know, but we call this breaking cleavage. So crystals can have a habit or cleavage. Cleavage is the tendency of a mineral to break along planes of weakness. Here's the mineral biotite. It has one plane of weakness, and it peels off into individual layers along a cleavage plane. The demonstration that we have here is going to be with halite. This is the mineral halite. Salty. Ugh, really salty. But good identifier of salt is if it tastes salty. So the mineral halite, notice how it has one parallel surface, another parallel surface, and if we turn twist, here's the third parallel surface. So this mineral has 3 planes of cleavage at 90-degree angles. Whereas calcite has 3 planes, 1, 2, 3. But notice this angle, it's not at 90 degrees. It's a little bit offset, smaller than 90. See that? Not at 90. Now what happens when I take my hammer and halite and I smash this halite into smaller pieces? I will do that now. Halite, hammer, smash. Let's give it one more. And it broke into 3 smaller pieces that all have flat surfaces, that still has 3 planes of cleavage at 90 degrees. Look, here's a little chunk that broke off. Same thing. 3 planes of cleavage at 90 degrees. This characteristic is diagnostic of certain minerals. Other minerals, like quartz, when smashed, they don't give cleavage, but they fracture. So, quartz crystal. This was a big piece of quartz. When it was smashed and broke, it broke very irregular with these circular wisps. This is called a conchoidal fracture. Halite, when it broke along planes of weakness. So quartz, we say, has fracture. Halite, or calcite, has cleavage. These are all very diagnostic, and it takes a little bit of practice to discern the difference between habit, cleavage, and fracture, but these are diagnostic properties of various minerals. I've talked about this, distinguishing cleavage planes from crystal surfaces. Special properties. So, taste of the salt. Salty. Characteristic. There's flexibility. Some minerals can be bent. Biotite mica, look at this. Bend. Whoa, whoa, whoa. Really bendy. Boing, boing, boing. Magnetism. Certain minerals have a lot of iron, are magnetic. Specific gravity. You have heavy minerals. You have minerals like talc that are soapy. Carbonate minerals. This is diluted hydrochloric acid, HCl. Certain minerals, like calcite, calcium carbonate, will react to HCl. So you see the fizzing or the bubbling? This is a reaction to the hydrochloric acid. So you may see, while exploring really awesome geology somewhere, a geologist with his side pouch pull out a little bottle of an unknown substance and pour droplets onto a mineral, and then it starts to bubble. Well, that is a test to recognize if that mineral is carbonate, most likely calcite, or dolomite. So minerals are identified based on physical properties, and this is because of their chemistry. It's because of their crystal structure and chemical composition. We have these various tests: luster, color, streak, hardness, habit, cleavage, fracture, and special. And we want to use all of them when we are attempting to identify a mineral. Multiple properties are necessary, and mineral identification is important so we know what mineral is what in order to get towards this question of how did the earth form? How does the earth work? Thank you so much. I'll see you again.